if it wasn't for the success of QED, for example, people wouldn't even try to build something like this, right? Now, the supposed success of QED is problematic. It's actually, falsified.
Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert D. Nameland, who has been the greatest living philosopher before me. In this video, I want to talk about my own unfinished PhD thesis, which I've never defended, and again, I've never finished it in the first place, which is talking about quarks, that is, subnuclear particles, you might say, the particles from which supposedly protons and neutrons are made from. So, let's roll.
Okay, so as you can see from my outline here, my PhD thesis actually takes up only a small part of what we're going to be talking about today, all right? But this is by necessity because the topic is very specialized, all right? So I need to describe at least the quark model in itself, like how it came to be, why do we need it, and do we really need it, etc., in the first place. So that's going to be most of what we're going to be talking about. And let me start with a brief epigraph, you might call it. So what are we actually detecting? Because some people have, not a very good understanding of, like, when physicists say, well, we detected this particle, like, what are we actually detecting? Well, as you probably can guess, most of our detectors are electric in nature, so therefore, whatever we can detect have to be able to either ionize something, that is produce electrons or ions or maybe some other charged particles, or it should emit some light or, whatever, UV or X-ray or gamma, whatever, photons basically, okay? So these are really the only particles we can actually detect, like directly, okay, with our detectors, because again, since they are electric in the first place. So those would be either the charged particles or photons, okay? And there's like different types of detectors. So many of the particles that physicists talk about never are detected for this exact reason. Like, for example, you cannot detect neutrinos directly because they don't have a charge themselves, they don't emit photons themselves, okay, so they have to interact with something else which emits photons or has charge, all right? So that's a secondary, indirect detection. Same goes for neutrons and many other uncharged particles. And at the same time, the particle might live not long enough to interact with the detector. Then again, you are left with only a secondary signal, all right? And even if we're talking about like the cloud chambers or bubble chambers, like what we see here is photons, but these tracks are supposed to be made by particles, which is kind of a reasonable assumption. But is this a direct detection of a particle? No, it's not. Like, it's photons that you see here, right? For example, like if this is a photograph of a bubble chamber, for example, right? You don't see the actual particle. You see the photons produced by some other particles, which this particle has interacted with, okay? So that's a pretty long chain of events that is, again, kind of is being oversimplified to a single detection act. So this is always useful to remember that there's very, very little stuff that we can actually measure, that we can actually detect directly. So this was my brief epigraph. Actually, there's a second part to it, which leads directly into the quark problematic, the quark problem. So in like 1950s and whatever, people have done many accelerator experiments. So for example, we accelerate like heavy nuclei and collide them together. We accelerate protons or electrons. We collide stuff together. And we see so-called resonances in some places. Like, what are resonances? So, for example, if I plot the energy that my incoming particles have before the collision, right? Well, I know this energy, okay, because I can make, for example, I can accelerate a proton to a certain velocity, I can calculate its energy, blah, blah, blah. And then we plot a cross-section, what is called a cross-section of the interaction that took place because of this collision that, again, my protons undergo. For example, protons, just for simplicity. What is cross-section? It's basically we're counting how much stuff is flying out of the interaction area. And again, I returned to here. What can we count? Only stuff that produces something like this, okay? This is what we actually count, and this is what is called cross-section. Just how much photons, electrons, protons, whatever we can actually measure is flying out of the area of interaction. This is called cross-section. I mean, I'm oversimplifying everything, but this is very close to the truth, so we can just consider it like this. So how much stuff is flying out versus how much energy was put in, okay? And sometimes we see these peaks. So at some energies, there's a lot of stuff flying out, okay? And at some energies, there's not a lot. And at some other energies, there's not a lot again. And these peaks are called resonances for understandable reasons, okay? Because this resembles some sort of resonance. Like something buzzes here really loudly, right? Like there's a lot of stuff flying out of the area of interaction. And people are considering, according to like quantum field theory and stuff like this, people are considering that this means that roughly around this energy, some new particle has been born, and all the processes that this particle can be involved in are taking place because this particle is being born, okay? And since there are many possibilities for this particle, this new particle, to interact with other particles, there's a big cross-section. So there's a lot of stuff flying out of the interaction area, okay? And these particles are literally called resonances, okay? Now, I give like big question marks here. Like, are they actually particles? Like, we don't see them. We see the stuff flying out of the interaction area. That's what we're seeing, okay? So whether they are particles or not is in my opinion, at least, like philosophically speaking, it's a matter of debate. Okay, so this is my epigraph. Like whether you like it or not, what I'm saying is like you can actually maybe come up with other ideas regarding that. But our current view considers them particles, and we'll just settle on this. However, my question marks remain, okay? This was my epigraph. If we still consider them, these resonances, as particles, we collide much of stuff together at different energies, and we arrive at so-called particle zoo. It's not what I've invented, it's an actual term. So the problem is that there's a lot of these resonances. Therefore, physicists say, well, there's a lot of new particles that we've created, again, in 1950s and 1960s, roughly, okay? And there's a lot of them, look at it. There's a lot of these particles, I mean, or supposed particles. Okay, let's just name them particles, okay? Because like I'll become tired of doubting myself at every step. Let's just give the story as it's been given usually. So there's a lot of them, as you can see. And it represents a problem, like why are there so many particles? And people have tried to explain this somehow. People have tried to build some sort of systematics between these particles, and it appears you can build some sort of systematics. For example, there is a so-called eightfold way, again, not my term. It's taken from gell-mann's paper. Gell-mann was one of the fathers of the quark model, quite an important figure here. So you can see that it's possible to sort of observe some sort of symmetry between all those new particles. All these are the particle names. These are like pi mesons, these are K, etc. I mean, all of these, basically, right? So there are certain symmetries between their like electric charge and other properties like spin, for example. And gell-mann proposed that maybe you can actually generate all this multiplicity from three basically smaller particles. I mean, not necessarily three, but let's say a small amount of smaller particles. And these smaller particles were called quarks, okay? So this is how the idea of a quark came into being. It's the systematics of resonances, which are assumed to be particles, okay, themselves. This is the prehistory of the problem, okay? And if you want to know the full history, I recommend this book. It's an absolute classic. I've read it, I've loved it, and again, I recommend it to you as well. Andrew Pickering, Constructing Quarks. Here we're not gonna go into all of this detail. What we are concerned with is that it took a while for people to actually accept the quark model because, well, people said, again, it's just a mathematical tool. Again, it's just a tool of systematizing the tables of all these new particles that we supposedly observe, right? We actually don't, you remember that, okay? Plus, there was a problem that quarks themselves are not directly observed. Again, we return here. Partly, though, only partly. And plus, quarks have some weird properties. Like, for example, the quark model requires so-called baryons to be made of 3 quarks and so-called mesons to be made of 2 quarks, okay? And the problem is that from 3 quarks, for example, you arrive at a fractional charge, fractional electric charge, like plus 2/3 or minus 1/3 or things like that. And it is kind of weird, right? By the way, I saw a complete BS explanations to why do quarks have to have fractional electric charge. Complete BS explanations online, but please read this paper if you want to know about it. Like, it's really easy to see from a simple system of mathematical equations like this. If you just write down the equation for a proton, assuming it's made of 3 quarks, and then for a neutron, assuming it's made of 3 quarks, you arrive immediately at the conclusion that the charges have to be basically 1/3 and 2/3 with minus or plus sign accordingly, okay? This is the explanation. And we don't see, particles with fractional electric charge. This is kind of weird. And by 1/3 and 2/3, I obviously mean 1/3 and 2/3 of the electron charge, or the elementary charge as it's called, okay? So yeah, we don't see the quarks. So maybe it's just a mathematical tool. That was the argument of the opponents of the quark model. However, still, after something like 10 or 15 years, in roughly 1970s, it was kind of accepted already. Like by the middle of the 1970s, it was kind of accepted already, the quark model. And why is that? Well, because the quantum field theory actually came to rescue, but we'll come to this slightly later. By now, what I want to say is that if you assume that for example, baryons are made of 3 quarks and mesons are made of 2. In order to satisfy Pauli's exclusion principle, so-called, I'm not going to go into any detail here, but I have to give you a reasoning of some sort, okay? So Pauli's exclusion principle is, by the way, I'm underlining here that it's a principle, okay? It's not even a theory, it's not a law, it's just a principle. So some criticism is possible here as well, but nevertheless, if we assume that it is true, then this is what follows. And what is the principle in the first place? It says that no 2 fermions can have the same quantum numbers, okay? What are quantum numbers? What are fermions? Like, I'm not gonna go into too much detail or it's gonna be way too long. And quarks are assumed to be fermions. So fermions have to have a half integer spin with respect to the Planck's constant. So yeah, again, a whole bunch of new terminology, but then again, I don't want to give you a brief textbook of particle physics in this brief essay of mine, okay? So in order to satisfy Pauli's exclusion principle, so no 2 quarks would be in the same state, would be described by the same quantum numbers, you have to introduce additional quantum number which they would differ in. Because if you stack 3 quarks together, like at least 2 of them would have to have the same quantum numbers, which is forbidden by Pauli's exclusion principle, and therefore physicists, in order to satisfy it, have introduced additional quantum number called color charge. Now, the name is completely arbitrary. It's called color just because in order to, again, satisfy all the statistics and Pauli's exclusion, you have to have 3 possible colors. And, I mean, 3 possible iterations of this number, let's put it this way, and the most simple that people came up with would be colors, red, green, and blue or something like that. So that's why it was called color. It has nothing to do with actual color. It has nothing to do with photons in the first place, okay? So yeah, there goes that. But it was called color charge nevertheless. And well, the word charge just means that the quark has it, just like it has an electric charge, but it also has color charge. All right. And then, as I've said, the quantum field theory came to rescue. Like QED, quantum electrodynamics, was developed roughly at the same time, slightly earlier actually, and it has had supposedly great success. Again, supposedly, like there's a big criticism recently in recent years of QED and its history and how it was essentially falsified, mythologized unnecessarily. So QED, quantum electrodynamics, is definitely not the most successful theory as it is being claimed. It's it's a myth, okay? It's a propaganda, if you wish. But again, this is not a topic of this discussion. We're talking about the strong interaction. We're talking about quarks. However, on the wave of this supposed success of QED came idea that, well, maybe we can build a similar theory for quarks, similar quantum field theory that would describe quarks. And QED works on U1 symmetry, so-called. It's all group theory, it's all mathematics, etc., etc. I'm kind of thinking like how can we go through with it without way too much explanations, all right? So let me put it like this. So group theory and quantum field theory that utilizes the group theory works with, check this out, imaginary rotations of imaginary objects in imaginary space. And supposedly from this, you can generate something that is actually observed, all right? Some properties of particles that are actually observed. I actually have a talk specifically about this, and I'm gonna link it in the description, this presentation of mine, and roughly somewhere here, you can see here, where I talk about group theory, local gauge invariance principle. I only mention it briefly, but the idea is there nevertheless, that we're dealing with imaginary rotations of imaginary objects in imaginary space. There is a principle of local gauge invariance which claims that you can actually generate the observed properties of particles in this way. Once again, I actually had to underline this, that it's a principle, it's not a law of nature, it's not anything fundamental really, it's just a mathematical tool which people use. It was exactly the propaganda about the QED, quantum electrodynamics success, that led people to believe that this is some sort of a big thing, you know. But since then, people actually use it uncritically, right? So if you ask a student, like a dude who just graduated from some sort of theoretical physics university program, they would tell you, oh, of course, local gauge invariance is it's how nature works. But they never criticize it. They never even ask the question, like, why do we even use it? Well, it's because everyone uses it, you know? Like, it's kind of a tradition, but nobody thinks about it, you know? It's a big question. We'll return to it at the very end, but for now, let's just say that, okay, it's a principle, like supposedly it works somewhere, and people have tried to use it for quarks. The group is much more complex than for QED, quantum electrodynamics, that only describes electron and a photon, essentially, and a positron, if you wish, which is like an antiparticle for electron. Here we have many more particles, but not only that, I mean, we have different quarks with different color charges. We also have many different gluons, so-called. Gluons are to quarks what photons are to electrons. So gluons are supposed to be the carriers of this interaction between quarks, which is called strong interaction. So today, in physics, we're considering that there are 5 fundamental interactions. I mean, 4 if you discount the Higgs. So that would be gravitational, electromagnetic, weak nuclear, strong nuclear, and again, Higgs. Whether you want to count it or not is up to you. So it's either 4 or 5, depending on how you count. And every interaction, as again, physics claims, is supposed to have like a boson, which is a particle with an integer spin, which carries it. So literally, the interaction itself is the exchange of these bosons. For example, electromagnetic interaction is the exchange of photons between charged particles. electrically charged. The weak interaction is the exchange of so-called weak bosons, for example, W and Z. There's actually no other, so it's not for example, it's just W or Z, okay? Supposedly, gravitational interaction is the exchange of gravitons, so-called, which are also bosons. I mean, supposedly it's because quantum theory of gravity doesn't exist yet, or doesn't exist, period, whatever you prefer. And in Higgs interaction, we have a Higgs boson, which carries the Higgs interaction. And in quantum chromodynamics, again, we introduced this term, which is dynamics of color, right? Chroma is a color in Greek. So why is that? Well, because quarks have color charge, okay? So in quantum chromodynamics, the theory of interaction of quarks and gluons, we have gluons as the carriers of the strong interaction. So these are bosons which carry strong interaction. But the problem is that gluons themselves should have charge according to this theory. So imagine if a photon have had electric charge of its own. So this would be the case, this is kind of the case for the strong interaction theory. So that's why it's very complicated, because again, if a photon have had its own electric charge, it could have emitted other photons itself. It could have interacted directly with other photons, but it doesn't happen. So the electromagnetic theory is relatively easy to build, and the strong interaction theory is relatively complex to build, okay? It's very complicated because the carriers of the interaction actually interact themselves, both with themselves and with the quarks, So it all becomes a big pile of nonlinear mess. So in mathematical terms, this group of symmetries that the strong interaction is described with is non-abelian. I'm not going to explain it to you. What does it mean? Mathematically, it just means that basically one element of the group multiplied by another, like A times B, is not equal to B times A. So if you change the elements, change the multipliers, the result will change, right? So 2 times 5 is not equal to 5 times 2. It's obviously not true for our, regular algebra, but it is true for non-abelian, algebras, which is the SU3 special unitary group 3 algebra. Okay, maybe that was a bit heavy on terminology, but by necessity. Actually, Pickering himself in his book is kind of apologizing. So he says that there's going to be a lot of weird terminology, a lot of bird speak here, but this is by necessity. It's because without even talking about this, it's going to be hard to even explain to you what the problem is. And in this video, we're dealing with the problem of quarks, okay? All right, so to summarize this, we're dealing with imaginary rotations of imaginary objects in imaginary space, and supposedly this gives us the strong interaction theory, as well as other interaction theories on the same rails of this local gauge invariance. And it's problematic, basically. Basically, it's problematic. But returning to my initial point, people were satisfied, all those, serious physicists, they were satisfied that you can actually build a similar to quantum electrodynamics, a similar theory for quarks. And that made people think hey, maybe we can build any theory. Maybe this is the path to, the grand theory of unification, the big theory of everything or whatever. So since then, people actually came on board and said, okay, let's use quark model, reinforced by this local gauge invariance formalism that we've, again, supposedly successfully used previously with QED, quantum electrodynamics, the theory of electrons and photons. So yeah, gluons have their own color charge. It's all very problematic. What's also more problematic even is that in QED, quantum electrodynamics, the interaction constant is small, which allows you to use a so-called perturbation theory. Again, I'm not going to go into too much detail, but it basically allows, again, supposedly, if you assume that QED is correct, infinite precision. So basically, every next term that you calculate reinforces your precision. However, here we have nonlinear theory with big interaction constants, so every next term actually potentially becomes bigger than the previous one, or at least is comparable to the previous one. So in order to calculate the result of a quark interaction process precisely, you need, roughly speaking, infinite number of terms, which is obviously impossible to calculate, and therefore people in practice have to use so-called non-perturbative methods, which basically means we have to dump all of this, okay? So we know, in air quotes, we know that this is correct, but we never use it because we can't, because we need infinite number of terms to calculate, all right? So we have to come up with some empirical models, basically very simplified models, which effectively ignore all of this in order to make our calculations in actual, strong interaction physics. And this again, it brings this fundamental question to life. Do we really need the quark model, at least of this sort? Maybe as a systematics is good, but if you do this and then you cannot calculate anything, it doesn't give you anything. You have to use other models anyway, non-perturbative ones, right? Do we really need this? The question is a good question, okay? Then there's another question, like we know we don't see any quarks in our detectors, even though again we're returning, we don't even see many other particles in our detectors in the first place, but still, we don't see any quarks, at least seemingly. No pun intended, okay? Why? Why is that the case? And this has become known as the problem of confinement of quarks. So supposedly, quarks do exist within a hadron, within a particle, such as proton or a neutron or pi, meson or k or omega or whatever, pick your, choose your fighter, right, from this list, right? So quarks may exist within these, but they are not observed, in the open, so to speak, in the field, alone, right? Why is that the case? This has become known as the problem of confinement of quarks. They are confined to this internal structure of a hadron, such as a proton, for example, right? So right now it's being described with only non-perturbatively, again, because you cannot solve the equations proper, because they require infinite number of terms to calculate, at least with perturbation theory. So you have to use some sort of empirical methods. And my PhD thesis is specifically aimed at explaining, in air quotes, confinement with the utilization of some other considerations, okay? But we'll get to that. Let's first describe this situation in more detail, the confinement, okay? So what are the evidence of quarks and gluons then? Gluons cannot fly away as well from within the hadron, by the way. So they're also confined. No quarks or gluons exist outside hadrons. So why is that the case? Well, because they strongly interact. They're strongly bound, okay? That's kind of the explanation. And the thing is, there's also this property of so-called asymptotic freedom. So within the hadron, they're actually kind of free. That's why it's called freedom. Asymptotic means like infinite. So when they come infinitely close to each other, they almost stop interacting, roughly speaking. But when they come apart, they start interacting very strongly. This is kind of a weird, I don't know, weird situation, let's put it this way. So when they are within hadron, they are free. But when they try to get out, they are confined, so they can't get out. What actually does get out is so-called hadronic jets. So when a quark tries to leave the hadron, it undergoes, again, all of this is supposedly so-called hadronization, all right? So it takes up, it creates essentially from a vacuum additional quarks and gluons and binds to them and you see a jet of, and not only that, like many particles are born, okay? And you see the jets of these particles. None of them are quarks, by the way. All of them are hadrons or other particles. Hadrons would be, well, think of protons or neutrons or these guys, all right? These are hadrons. So we don't see isolated quarks or gluons, we only see aggregates thereof, which are hadrons. And in the form of jets specifically, okay? So how does this hadronization happen? How does a bare quark, so to speak, is being dressed up in this coat of other particles? This is the problem of confinement. This is the problem of hadronization. This is the problem my PhD thesis is devoted to, okay? But, so finally, we arrive at the topic. So this is the title. It's the behavior of colored particles in stochastic vacuum of quantum chromodynamics. So we're dealing with this, essentially, but we are using a sort of non-perturbative model. So we're using sort of an empirical model of this stochastic vacuum. Now, what is vacuum in quantum field theory? Like not many people realize, but literally by definition in quantum field theory, a vacuum is not an emptiness. A vacuum is the main state of fields. So supposedly, according to quantum field theory, everything, everywhere, like literally every point in space, there are all kinds of fields there. But in a vacuum state, they have no energy. So they're in this lowermost state. This is called vacuum. When the field is there, but it has no energy, it's not excited, okay? And when you excite it, when you give it energy, then the particle is born. And which particle depends on which kind of field do you excite. The electron field will give you electrons. The electromagnetic field will give you photons. The some sort of quark field will give you some sort of quark, okay? This is the fundamental view of the current quantum field theory, the fundamental view of reality. The fields are everywhere, it's just that mostly they're in a vacuum state unless there is a particle, in which case the field is excited. That's how it's described. So stochastic vacuum is this sort of phenomenological, i.e. empirical, i.e. simplified model of a non-perturbative character of how you can describe quantum chromodynamical effects without having to deal with, you know, this infinite number of terms to calculate. So again, it's a very simplified model of quantum chromodynamics, specifically of the vacuum thereof. So it basically says, let's consider, I'm oversimplifying again, let's consider the vacuum of quantum chromodynamics as a bunch of, let's say as a thermal reservoir, let's put it this way. It's just a big system with a lot of degrees of freedom, okay? Just a lump of stuff, let's put it this way. Even though it's called a vacuum, as we've said, there are all kinds of like fields present, specifically the strong interaction field, the field of gluons and quarks is present there nonetheless, even though it may not have energy, but it's still there, okay? And by the way, this is the draft of my PhD thesis that I've never finished, as you can see. Let's just kind of skim through it. Wait, put so that you just can see how much stuff I've written. This is like a literature review, blah, blah, blah. This was all done before the chatbots, so I've written it all myself. Just so you know, it's not like I've created it yesterday or something. So it's 2017, as you could have seen at the title page. So yeah, there's a lot of stuff. We calculate density matrices. We calculate like some quantum informational characteristics. So let me give you a brief idea of my thesis in 1 minute or less. You can actually, so imagine we have a hadron like a proton and there's a quark inside of it. So if we try to kick the quark out of it, so we give it a lot of energy, we hit it with a super fast electron, for example. Okay, so it tries to fly out, but there's this QCD vacuum everywhere, you know? There's like dormant virtual quarks and gluons sitting everywhere. And they interact with this guy, okay? And when they interact with this guy, like he had a color charge. Let's denote it with a red color, okay? But during this interaction, it's happening through exchange of gluons, which carry charge, okay? And they eventually, as it flies through this vacuum, they strip away his color, so to speak. So the color gets distributed over the whole stochastic vacuum eventually, and at some point, this guy has no color anymore. So this is how we describe the loss of color and therefore the inability to detect a single quark. Of course, in practice, it would mean it has caught some other quarks from the vacuum itself, and it has turned into a hadron, or maybe a hadronic jet if it had a lot of energy. So it can bring forth many hadrons, maybe a couple of mesons as well, with only 2 quarks, etc., etc. So this is a hadronic jet that we observe. This is my PhD thesis in a nutshell. We introduced this stochastic vacuum as like a reservoir with a lot of degrees of freedom, and as the quark moves through it, it loses its charge, so it gets distributed over this big reservoir. So you can never pull it out of it, okay? Because it's so distributed. Again, entropy rises, you know. We describe it all in quantum information terms. So we introduce the usual like measurements like entropy and things like that. Let me show you. This is purity, fidelity, like these are usual parameters that people use in quantum information theory. And this is the entropy, blah, 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 blah. Yeah. I'm kind of glad I didn't finish this work because, again, already when I was working on it, this draft was finished in 2017. As you can see, it has like 66 pages or something. So it's almost done, like maybe 20 more pages and I would be done. And then I just defend it and I get a PhD, but I didn't. And it's kind of fine because, again, right now, I just think quark model is wrong in the first place. Not wrong, but useless, more like useless kind of wrong. Because even though, as we've said, it allows us to build systematics. So it is fruitful, let's put it this way, to have an observation that you can maybe like build all of these resonances if you consider them being particles in the first place, because a big criticism is possible even here. But still, if you consider all of this being correct, like it is useful to consider that you can actually build all of this multiplicity from a relatively small amount of particles, all right? And it's a useful insight. But when you add this crap, which is non-justified in my eyes, again, see the history of quantum electrodynamics, which I haven't considered here, like, do we really need anything bigger than just the observation of possible systematics? Well, some people might argue that we do because, well, what are the other models? Do we even have any other models? And we do, actually. Like, there are alternative models. They're just relatively unknown just because of, you know, the sheer amount of resources that's devoted to this model, because it's taught everywhere, right? The quark model. It's supposed to be correct. It's supposed to be like the universe is built like this and blah, blah, blah. This is a law of nature. We have fundamental interactions. We have quantum fields. But all of this is just a model in my eyes, okay? And there are, I know of at least one alternative model, which is based on nonlinear electromagnetism. But I'm not gonna, I mean, obviously this video is not the topic of discussion for such a model. But there are some models which are at least maybe not plural, but I know of at least one, which is really good in the sense that it simultaneously shows you a realistic picture of a hadron, such as a proton or a neutron. And it also explains why we actually deal with some sort of rotations. So principle of local gauge invariance sort of arises there naturally, okay? And we like, and some other properties such as spin are explained in air quotes, but at least, like, you know, some hints are there, because in quantum field theory, nobody knows what spin is. Like, it's just some sort of angular momentum present within the particle. Even though the particle itself is point-like, considered to be point-like electron, for example. It has spin, but it's point-like. How does a point-like object can have angular momentum? Like, what are we even talking about? It's a bunch of bullshit, no? Isn't it? Like, what are we talking about? Yeah, so there you go. There are alternative models. I mean, if you ask me well enough in the comments, maybe I'll make a video about at least the one that I know about. But there are. Let's just, you'll have to believe me until now that there are alternative models, and they are not being developed just because first of all nobody knows about them, and secondly there's a big competitor, big fat competitor that's been eating for what 50 years, 60 years that QCD have been in development, quantum chromodynamics. Yeah. So the main takeaways here is that quark model is only a model unless you undergo this what I call Galileo's curse. It's in this video what physics is and isn't. I talk about Galileo's curse, which is again the inability to recognize your model for what it is, i.e. just a model. So Galileo was prosecuted for what? For saying that the heliocentrism is the truth. Where the cardinals, the inquisitors were telling him, no, it's just a model. It's not the truth. And Galileo said, no, it's the truth. So it is only a model. I'm sorry. Just as well as heliocentrism is only a model, okay? So the inquisitor was correct. Then big criticism is possible here. Again, why are we dealing with imaginary rotations of imaginary objects in imaginary space? What does it have to do with physics? What is the ontological status of all of these procedures? Okay, they may be mathematically captivating because they're kind of cool, you know. You kind of generate particles out of some abstract stuff. It's kind of cool. But in practice, again, if you look at the history of QED, even quantum electrodynamics, it is problematic even there, okay, and highly problematic. Not even talking about this, where we can't even calculate anything precisely, okay, because of the big interaction constant. Actually, like, it depends on distance, so we have asymptotic freedom. You can calculate stuff within the hadron, where the quarks are relatively free, because there the interaction constant becomes near zero, and you can do the calculation kind of the same as in QED, but that's a whole separate story. But yeah, then you can criticize this whole issue. This is another way of reasoning. Maybe you can arrive at some alternative models where these resonances aren't even particles, but maybe they are resonances proper. Maybe, I don't know, some sort of oscillation is happening, some sort of waves are being born. I don't know. I mean, it's all grounds for development of alternative models. There are big problems, again, since, again, we can't really calculate anything, right? There are big problems, like people cannot even calculate the proton radius. People cannot calculate how proton spin arises. By the way, when we're talking about quark model, there are so-called constituent quarks, and these are, for example, up, up, and down for proton, or up, down, down for neutron, right? But like, these are constituent quarks or valent quarks, but there's also so-called C quarks, which are supposedly actually the majority of the proton and neutron. And there's like infinitely many of them, okay? Like if you if you add the masses of 3 quarks that make up a proton, you don't get a proton mass. It's actually much less than a proton mass. And it's the addition of these C quarks, as they call, literally C quarks. There's a sea of quarks, okay? And it's taken from the same idea that there's a vacuum and it's getting excited here and there, you know, and you get these like semi-virtual quarks, but which have energy nonetheless, okay? And they're called C quarks. And gluons, by the way, they're constantly exchanging these gluons, etc., etc., etc. So it's all very, very problematic, you know. We cannot calculate things like neutron lifetime. We can't even measure it, as you may know. Okay, there's like 1% how do you call it, error at the very least, right? 878 seconds or 888 seconds. I think I briefly touched upon this in this presentation of mine, but I don't exactly remember. It's not a topic of this discussion anyway. And yeah, let the dead bury their dead. Like, what do I mean here is that people will undoubtedly keep working on this just because they've been working on this for 60 years. But it's their problem. Don't make it your own problem. Like, you can see how flawed it is initially, like how weirdly built it all was. Like, if it wasn't for the success of QED, for example, people wouldn't even try to build something like this, right? Now, the supposed success of QED is problematic. It's actually, falsified. So this is not even needed in the first place. And even if you do it, you still cannot do anything with it. You still cannot calculate anything. Do we really need this, right? That's my question. So people will undoubtedly, again, keep working on it, but let them work on it. Again. If you ask me, my opinion, you just work on alternative models and you let the dead bury the dead, okay? Once your alternative model will become strong enough that you can build, let's say, some sort of experimentum crucis, the crucial experiment, or you may propose some sort of new observations. Just like these guys have some sort of observations which allowed them to build their model, so can have you. And honestly, if you ask me, it's probably not very hard, considering like how shit this model is. All right, the Quark model. But nonetheless, hopefully I gave you at least an overview. Like, I understand that there have been a lot of weird terms. If you don't really understand anything, I mean, you can ask me in the comments always. I'll try to clarify. But I'm not sure I'll be able to, because again, even Pickering complained how much of a bird speak there is.
Now, as you can see, even though quarks remain a pretty useful, or maybe, I don't know, convenient vehicle of describing the statistics of hadrons, like, all of this is so model dependent, and since the quarks themselves are never observed in the free state, like, one still may ask a question like, do we really need the quarks? Maybe there are other models, and I've actually shown you that there are other models which do not require any quarks to exist, and at the same time, like, explain, like, whichever you prefer, that the quark model, like, explain basically why the quark model can actually arise from whatever we observe, alright? So yeah, hopefully you've learned something today. Maybe you didn't. Well, then I apologize, but whatever. Whatever. Once again, hopefully this all reinforces my point that physics does not study the world. Physics studies models of the world, alright? So yeah. Unless you are cursed like Galileo, right? Unless you consider your model being the truth rather than just a model. Thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.